What's Boyle's law?
P2, V2. Good. What is Charles's law, Ariana? Okay, so Boyle's, Charles's. What's Avogadro's law, Maddie? Okay, and whenever you're saying these variables, you know all other variables are constant. Yeah, just those variables are changing. Who's Gay-Lussac's law, Tyler? Okay, and then combined gas law combines a couple of them. Okay, so we're going to talk about these a little bit more today, but basically you need to know whose law is what. So if I say Boyle's, you say P1, V1, P2, V2. If I say Charles's, you need to know what it is. Okay, so when I say those, you need to know what variables are involved because you want to be able to quickly do these problems. But I think that after doing those problem sets, it really have to kind of solidify what those gas laws were. When you did 5 problems of each one, you feel like you know them pretty well. What conversion did you always have to make sure you did before you plugged in? Celsius to Kelvin. Pretty much any of the other ones are fine. You can use millimeters of mercury, you can use kilopascals, you can use atmospheres, you can use any of those pressure units in any given gas law, right? As long as they're the same pressure units throughout the problem. The only one that you never can put in is Celsius. You have to convert to Kelvin, but on my answer key, I may have to convert it back to Celsius to fool you, because when we get our next unit, we are allowed to use Celsius for what we're doing in thermochemistry. So I'm trying to drive into your head. If you see Celsius and you're doing gas law, you got to go to Kelvin. But if you're doing like something in our next unit, thermochemistry, you're good to go. Okay, still got to fix it. So I have the key for problem set 13 up here. I'll go over that with you in a little bit. But we're going to take notes first, and then we'll go over some more practice. The board's just being silly. Okay, so, yeah, questions? I will after I finish checking people. I'm almost done. Yeah, I'll go over it at the end of it. All right, so who in their grand knowledge knows what a theory is? What's just a theory? Just any old theory. What does it mean? Giselle, tell me what you know. Okay, so something that explains why. Okay, so what we have theories and we have laws. Give me an example of a law. Newton's law. Okay, just like for every reaction, there's an opposite reaction. For every reaction, there's an opposite reaction. Can I explain anything with that law? For every action, there's a reaction. Did I explain anything, really? No, I was just like, hey, this is what it is. Guess what? Stuff falls. The law of gravity, stuff falls. At 9.8 meters per second squared. But I'm just a statement. Okay, so a theory is really a big, long explanation that's going, really supporting why you're saying what you're saying, right? So here's what a theory is. And in chemistry, we always call them models because we have, like, the, let's say, the VSEPR theory. What's the VSEPR theory from back in the day? VSEPR. Valence, shell, the electron pair, repulsion theory. We were like, oh, hey, there's these electron pairs on the atom. They repel each other. They push around the bonds. They make tetrahedral shapes and trigonal planar shapes and bent shapes and linear shapes. So it goes on and on and on, right? You're theorizing and you're making a model out of it. If you need a pencil, stop bothering the girls. Lordy. So we want to talk about this in terms of a model because we like theories because they kind of help us stay on a straight path when we're explaining things. Okay, so the kinetic molecular theory is the theory that we choose to use for gases. Kinetic molecular theory. So we're talking about, what does kinetic refer to, do you think? Huh? Like kinetic energy, so we're talking about motion. So we're talking about motion or moving. Molecular, what does that refer to? Molecules, right? Molecules, not ionic stuff, not like salts and stuff you put in aqueous solution. We're talking about gases, right? So molecules, which are generally non-metal, and we're talking about a theory. Okay, so ideal gases. That word ideal, what's that mean? Or hey, raise your hand if you feel like you are my ideal student. You feel that proud about yourself. You are my ideal student. Nobody? I got some in here. I got some hard workers. People who try for me every day, who attend their homework every day, who study, look through their notes every day, who come to class every day, who are smiling and answering my questions and excited about chemistry. There are a couple in here. Now, man, if I could like mesh a couple of you together, I would really have the ideal student, right? So, close your eyes and think about your ideal man or your ideal woman. Think about it. All right, so they go home and they cook. They make some good food, right? They take you out at night. They buy you stuff. They hold your hand when you're walking. They tell you how nice you look every day. They compliment you all the time. Okay, so you're thinking ideally, right? Now, in reality, does that perfect person really exist? I mean, let's be real here. Like my husband, he makes coffee for me every morning, but today's coffee was kind of weak. I'm spoiled, okay? He makes coffee every morning. But I'm not going to tell him it's weak, right? Because I want him to make coffee for me every morning. Because if I complain, I don't get coffee. I need coffee, okay? So the ideal person may not exist, but we can assume they exist to make our life easier. Because if not, it's hard to live a life where you're like, man, there's got to be something better out there. You just got to go with it, okay? So we're talking about ideal gases. Do you think they truly exist? No, okay? They really don't exist, but we assume they exist to make our lives, our chem lives, easier, so we can go with something called the ideal gas law. It's basically we're lying to ourselves just a little bit so we can do math problems easier. Are you cool with that? Lie to ourselves a little bit, make math easier. Yeah? Okay, so the postulates, the 5 things we have to know about the ideal gas law, about the kinetic molecular theory are these. We say that ideal gases have no volume, meaning if I have, let's say, a 5-liter container, and I assume that the volume of individual gas particles are so tiny, I just call it negligible, like, it's not there. That means that those gas molecules have a whole entire 5 liters to move around. Okay, but does mass have no volume? No, that's a flat out lie, right? But it's a little bit, if we assume that they're almost zero, it makes our math so much easier. So, what do you think real gases have? They have volume. Okay, that's easy, right? They have some sort of volume. So if those real gases, the gases that really do exist in that 5-liter container, they might only have, let's say, about 4.95 liters to move around in. Versus a full 5 liters, they only have a little bit because they're taking up the part of the space that they can't move in, right? Like they can't move if they're taking up that space. So they're taking up like the 0.05 liters of the whole container. Okay, so more ideal gases. Ideal gases are in constant random motion. Constant random motion. And when they're in constant random motion, that means they do not interact with one another. So I'm going to put INTX, interaction. Looks like interaction, right? That's my abbreviation for interaction. Go with it here. Okay, so gas particles are not interacting with each other. They're randomly moving about. Now, that's probably not 100% correct. That's probably a lot of it correct because, gas particles here, they're everywhere, right? They're really far apart from each other. But what if I'm a polar gas molecule and I'm moving around, a polar gas molecule, and I come across another polar gas molecule? What are we going to do? Polar and polar, like dissolves like, that's the dissolving one, right? But polar and polar actually interact maybe through hydrogen bonding or dicyclic interactions, right? So if I find another gas molecule with a polar, we're going to stick together like glue, like, hey girl, what you doing? And that's about it, okay? But if I'm a polar gas molecule and I find a non-polar gas molecule, I might not interact because we are not the same in terms of our intermolecular forces, right? So we say that they don't have to interact, but they do, okay? They actually do interact with IMFs. I'm abbreviating here, okay? So make sure you catch on what I'm saying. Because they just naturally do have some attraction to one another. Okay, more. Ideal gases have elastic collisions. That means if two particles are zooming towards each other and they've got energy to them, and they hit right here in the middle. They collide in the middle. What we would normally assume with ideal gases, we would say they bounce back, hit each other, no energy is lost. They have the same velocity they were coming in with. They just bounce backward and go the opposite direction. So elastic is like, think of a rubber band. It stretches, it hits, and it comes back out. You can always stretch it back. We're assuming that no energy is lost in that collision, though. You know what assuming does? We all know you can't assume all the time. So what do you think real gases do? When they collide, what happens? They lose just a little bit of energy, okay? So collisions, all right, it's a different color. Collisions result in loss of kinetic energy. And I'm going to put in parentheses friction. Friction is actually when they hit each other and they kind of like scooch together a little bit, the friction is what causes them to actually lose energy. Next, okay, so there's like a bunch of little details about the kinetic molecular theory. I told you explanations are long. They're not like laws. They're long and detailed. Let's touch interactions, yeah. Okay, for ideal gases, kinetic energy is proportional. So kinetic energy is proportional. The little fish thing means proportional to Kelvin temperature. True or false? Did we talk about that last week? Yeah? We talked about energy. So kinetic energy, if you heat up something, they move faster. Okay? Kinetic energy, if you heat them up like a microwave, they're bouncing around, they're vibrating like water molecules. It's just that the microwave is actually what's heating them up, not just truly temperature or heating it up. So this is always true, okay? I don't care if I'm real gas, fake gas, pseudo-ideal gas, whatever. Always true, okay? So this statement is true for everything. That's one that we're not lying to ourselves on. So for an ideal gas, kinetic energy is proportional to Kelvin temperature. So if I increase kinetic energy, if I increase temperature, I'll increase kinetic energy. They'll move faster. And then lastly, this one's related back to this one. We kind of talked about this already, but we assume that ideal gases do not attract or repel each other, aka no IMFs are involved with them at all. But, you know, we know really in the real world, not La La Land on paper, you know, polar will interact, polar molecules, and so forth. That's just an example. But what I'm saying is IMFs do exist. I don't care what kind of gas you're calling it. But these are just assumptions we make to make our math easier. Trust me on this one. I've done the real gas laws, and they're not as fun as our ideal gas laws, so we get to assume a lot of easy stuff here. Thumbs up when you're done here. And then just BT dubs, you guys can hold on to the your test papers for now. The actual test that you guys took, I have to use for my second period, so just don't take that with you. You guys can leave that in your desk today. And I want your like Scansion stuff back in probably like 2 or 3 days. Okay. So here's the graph that represents gas law, or represents something called the ideal gas law. Okay. So give me your box of air again. I'll tell you what to write in a second. Give me your box of air. Okay. Let's assume our gas molecules are hanging out, they're floating around, they're randomly moving, they're not interacting, they have no volume, they don't interact. Yeah, so that's pretty much what the kinetic molecular theory says. If they don't do anything, they just hang out by themselves, right? Now, increase your pressure on the box. Now, you've scooched the molecules together. What do you think they're going to start doing with each other? Okay, no longer we spread apart, we're like super close together. What are we going to do? Hey girl. Let's interact with IMFs, right? So they're going to start interacting, right? Increasing the pressure and pushing those gas molecules together forces them to interact, okay? Now, take your box of air, okay? Now, what happens when you cool down the gas molecules? They're normally moving really fast, right? Because gases are really spread out really fast. If you cool them down, what's going to happen? They slow down. So even if I don't want to interact with somebody, but we're both moving really slow, they're like, oh, darn it, we're attracted because you're just moving so slow. Naturally, the IMFs are going to kind of come into play when you're moving slow. hey, if you're moving at the speed of light and you're like zoom past each other, do you really have time to interact? You're zooming past each other. No. So these two conditions are very, very important because those are the conditions in which real gases start acting like ideal gases. So real gases that really exist in the world start acting ideally when they are compressed under high pressure or when they're moving slow under low temperature. Because that's when the IMFs really come into play and they start to kind of force intermolecular forces and force them to interact with each other. So those two conditions are where real gases start to act like ideal gases. So we call that acting or behaving like real gases. Come on. All right, so you can see that occurring here on this graph because we're going to assume this is the ideal line. That's the ideal kind of dashed line is ideal. And I'm going to show you my axis here. On the bottom, it says pressure, okay? So increasing pressure, what happens is I go from here on pressure all the way over here on pressure. What's happening to these other lines? Are they staying close to the dashed line or are they going farther away? Huh? They're going farther away. So what this is called is as I increase in pressure and these gases, there's nitrogen, methane, hydrogen, and carbon dioxide, they're getting farther away, right? They're deviating from ideal behavior. Because I'm increasing that pressure on them, I'm making them interact. So just like we said, increasing pressure and slowing them down, aka cooling it down, will deviate from will cause ideal behavior. Deviate from ideal behavior. What did I just say up here? I just said act ideally. Sorry, I'm forcing them to not act ideally. I meant deviate from ideality. Deviate. Meaning they're not ideal under those conditions. I'm forcing them to interact. Sorry about that. I wanted to show you the graph first and then I went ahead and talked about it first. Okay, so do not write down all of this. I want you to write down these bullet points of details, okay? So we know that the kinetic molecular theory explains a lot of stuff. Well, the properties that we already know about gases, it helps us to support our thoughts. We know gases have low density. What does that mean they do in our classroom right now? Are they going to sink? They're going to float, right? They're floating. They're not like sinking to the ground. If not, we'd all die because we need the oxygen up here in our faces. Right? If the oxygen wasn't floating, we'd be in big trouble. So we know they have low density. And this kinetic molecular theory supports that. All these little statements they say support that thought. We know we can compress gases. That's why I've been making you have your little box of air and smush it. We know we can do that because there's, gas molecule here, here, and here. What's between them? What's between like gas molecule 1 and gas molecule 2? From here to here, there's just a lot of space between them, right? There's nothing between them. So you can smush them together. You can compress them. You also know you can expand gases. You can make them move farther apart because they don't hang out together a lot. You can make them expand. And this will, parentheses are just basically defining what compression and expansion means, but I think you guys know what that means. You guys remember diffusion? Biology? Yeah, totally. Diffusion is the movement of particles from what concentration to what concentration? High to low, good. So diffusion goes from a high concentration to a low concentration. So you already know that happens. So if I brought in, a big huge box of Krispy Kreme donuts, I brought them in, who would smell them first? Me. This side of the room. And you guys your stomachs start growling, and your mouths will start watering, and I could go closer, but over, a span of 5 minutes or so, all of the particles, the scent particles that are hanging out on the donuts, they start to diffuse out from their high concentration box to a low concentration noses, right? So we know that happens. Now, the molecules of Krispy Kreme scent molecules, They're really tiny. That's why they can move so fast. But if I brought in, I don't know, something that was really heavy, a heavy molecule, it would move really slow. So I'm going to give you a little bit more information on this one, and this is the equation for it. Write that equation down. KE means what? Kinetic energy. 1/2 m, which is mass, and v, which is velocity. Speed. Velocity is speed, okay? So the equation is 1/2 mv squared. So if you think okay, so I'm talking about my brother here. He's a little skinny dude. He was a runner. No, was he a runner back? Yeah, running back. Wide receiver. Wide receiver. Totally wrong that one. Okay, so he's a wide receiver. He could jet. He could make it down the field and totally, touchdown all the time. One time, what did he do? Somebody tackled him at the field goal line and made him like jam his elbow down, his whole ulna, and the radius came out of his arm like this. It was pretty. No, it was this way. I think it was this way. But yeah, he's had to sit out for a couple games. But anyway, he was little. Okay, his mass was little. What did I tell you about his speed? Fast, man. He's fast. Okay, so basically what this means is smaller molecules have a super high speed because they're just so small. But the hiker, the center, he was not going to go down the field and get the ball. Sorry. He had a job. It was not that. Because he was a little bit more massive, he was not going to be very fast running down the field. Not saying he couldn't, but that was not his job. Was not made for that. So pretty much increasing the mass does what to the speed? Slows it down. And decreasing the mass does what to the speed? Speeds it up. Okay? They're inversely related. That's what we need to know about diffusion. So fat molecules move slow, little molecules move fast. All right, and then the last definition, this was one from your problem set 14. Effusion is similar to diffusion, but effusion means coming through like a small hole. So if I have a balloon and I poke a hole in it, those molecules will be escaping through a pinhole, and their rate, how fast they move, their rate, depends on their molar mass. So like I just said, who's going to move faster? Helium or carbon dioxide? Why helium? What's the mass of helium? So 4 grams, is it 4 grams? Yeah, 4 grams per mole. Carbon dioxide weighs 44 grams per mole if you add it up. So smaller things move faster. Thumbs up when you're done here. Okay, so those are just some details. Those are assumptions that I think are very common. You guys know a lot about gases already. Okay, so now, why in the heck are we talking about the kinetic molecular theory today? Because we are talking about the ideal gas law. This is the last gas, or not quite the last one, but this is the last big one you guys will learn about, okay? The next two that we'll learn about tomorrow are pretty simple. So, we know the kinetic molecular theory supports our ideality of gases. We have an equation for that, people. It's called PV equals nRT. You write this down in your reading guide 14. You have to write down this gas law constant as well. It's super duper important. I'm going to make this darker. I'll give you guys a second. Yes, question. Wait. Okay, I'm gonna finish this for you guys. I just need to. Okay. So, we know a lot about gases. We know a lot about their variables, right? Now, the ideal gas law is going to help support us in our thoughts of the kinetic molecular theory. We can only use this law when it says is ideal. Okay, it has to say ideal, or it can give you information like this. No second pressure, no second volume, no second amount, no second temperature. If you're given one of each of these, or close to one of each of these, not two of them, then this is the only law you can use, because all of our other laws had two pressures, or two volumes, or two temperatures. So it's very clear when you're supposed to use this law, okay? So we have to use this constant as well. So PV equals nRT is the law. The P must be in atmospheres. So if you're given millimeters of mercury, let's say I give you 100 millimeters of mercury, how are you going to convert to atmospheres? 760, good. 1 atmosphere is equivalent to 760 millimeters of mercury. So then you would convert from millimeters of mercury to atmospheres for an ideal gas law because you cannot use anything else, because look, this R value, this constant we have to use, has atmospheres in it. So we have to agree with that those variables. Volume then must be in what according to the gas law constant? Liters. Amount must be in moles, not grams. I might give you grams, but you got to go to moles. And temperature must be in Kelvin. Okay, so pretty much all of these match those units there. Now that is one big honking constant, so I'll practice with that one with you. All right, so on your gas laws, yeah.
What is that? 0.081.
That's the constant number. So it's like, how would you write this out? You would write it out like R is 0.0821 atmosphere liters per mole K. So this is the constant that's like is in the numerator of this particular value. Okay, so let's do a practice problem with this with the ideal gas law. On your problems, we just did 1 through 16 for me. We're gonna do 17, 18, 19. Okay. So pull those out for me, and I'm gonna do 1 or 2 with you, and then you guys can do the last one by yourself. So the first one states, you don't have to do these, so I'm doing this one with you. Okay, now, last week I modeled for you on how I want you to start these out. I'm asking for you to do the same here. So these are the answers. I'll pull this back up for you in just a moment. I just need some space right now. Okay, 17. Here we go. A student collects, stop, what am I writing? Volume is 425 milliliters of oxygen gas. And I'm just writing it because it says oxygen. It may not matter here. At a temperature of, what am I writing here? T equals 24.0 degrees Celsius. At a pressure of, P, pressure, 0.889 atmospheres. All right, so we got lots of information from one sentence. Good. Question. How many moles of oxygen? So I'm going to put question moles. Now, but what's the value for moles, or what's the letter for moles? N, right? So question is N. I'm looking for moles. So how many moles of oxygen gas did the student collect? And then the second question is how many grams of oxygen gas did the student collect? So which question do you want to try to figure out first? Moles, because we can always convert to grams. Like, we have that awesome power using molar mass to convert to grams. All right, so you'll notice I got 1B, 1T, 1T. I don't even have to look at the paper anymore. What law do these variables occur in? Ideal gas law, right? So PV equals nRT. We know R, we actually do know it. I will always give you 0.0821 atmosphere liters per mole K. I will give you that value. But you just have to know where to put it, right? We know temperature in this case, we know V, and we know P. So we're solving for N, right? So that makes sense. Let's rearrange this first. So how do I want to solve for N? What do I have to do to isolate this? Good, divide by RT. Okay, so my total, like the new equation that I'm going to be plugging into is moles of oxygen. I'm just going to put like a little O2 down there to say this is moles of oxygen in this case, is equal to PV over RT. Okay, I've got to do some minor adjustments before I can plug in though. Is my pressure in the correct unit?
Yeah.
Yes, atmosphere is good. Is my temperature in the correct unit? No. So what am I doing here? Add 273 to 24. You can do that in your head. 297. Thank you. All right. Is my volume in the correct unit? No. What do I need to do? So divide by 1,000, go to liters, so move the decimal back. How many places? 3. So this is not 425, this is 0.425 liters. And moles will be in moles when we get there, okay? I'm going to write the R value up here. 0.0821 atmosphere liters per mole, okay? So we can remember to use it. All right, let's plug it in, plug it in. So this is exactly the same methodology. Write down your knowns, write down your formula, rearrange it if needed, and then plug in. So the moles of the oxygen is equal to P, plugging in 0.889 atmospheres, times the V, 0.425 liters, over, I like to put parentheses so you just remember that those are separate things there because we get a lot of units up in this one. R is the big honking one, right? So here I'm writing it. 0.0821 atmosphere liters per mole K. It's a fraction in the denominator. Deal with it for now. I'll cancel out units in a second. And T, which is 297 Kelvin. Okay, so basically this is a fraction in the denominator. And the first unit, I can see that cancels. Atmospheres, good. So I have an atmospheres in the numerator and in the denominator. What else? Liters in the numerator, liters in the denominator. Good. And do you see that this Kelvin is in kind of the numerator of the denominator? And this is in the denominator of the denominator? So those can cancel as well. So Kelvin and Kelvin cancel. So what's the only thing left? Moles, right? So moles is left. I know it looks like it's in the denominator, but it's in the denominator of the denominator. It actually goes back up to the numerator once you do all your division out. So we're in moles. Happy with that because that's what our question is asking. So when you plug in your calculator, please, please, please do this times this, and then divided by either parentheses, this times this, parentheses, or get both the numerator and the denominator and then just divide them. So practice that for a second and tell me what you got.
Wait, what you say? So the top two times each other.
Yep, so multiply these two equals divided by parentheses. These two multiplied parentheses. Just make sure you put parentheses if you don't multiply them, or you can just get this first thing by multiplying the first two values, and then second, get these two by multiplying them, and then take those two values you got and divide. Okay. Just making PEMDAS is at work here. PEMDAS. What'd you guys get? .0155. 0.0155. N is equal to 0.0155 moles of oxygen gas. I'm writing oxygen gas diatomically, remember, so don't forget that. Okay, so we got our N value. How do we get to grams? What's the molar mass? 32. Thank you, Lord Jesus. Because we keep saying 16 on our papers. It's because we look at oxygen and we don't think about its diatomic nature. It's got two of them, right? So 16 times 2, 32 oxygens. Okay. So then that times 32 will give us our grams, which is 0.495 grams. Okay, so this was our first answer. This is our second answer. I'm going to leave this on the board for you. I want you guys to start number 18 for me, and then I'll jump in with you. Start number 18 for me. Starting number 18, how's it going? It's going. Yeah. No, it's only the N is mold. So stay with you. I'm starting the problem on the board if you need some help. Knowing your isolating P, you know PV equals nRT is your formula. You need to divide by V on both sides, which sets you up for success with this little derived formula, I guess. And then once you've labeled all your values, you plug from there, okay? Though you just have to make sure you go to Kelvin, so that's 298 Kelvin. And everything else is in the given unit. Now, pressure, it says it's asking for kilopascals, but we know our pressure we solve for over here is going to be in what unit? It's going to be in atmospheres because that's where our value is. It's got atmospheres in it. So we know we're publishing first in atmospheres and we have to convert later to kilopascals. So your moles and moles cancel top and bottom. Your Kelvin and Kelvin cancel top and bottom, just moved out by accident. Your liters and liters cancel top and bottom. You're stuck with atmospheres, which is what you wanted, so you know you set it up correctly. That pressure is I accidentally just moved it, but it's right here. This is Kelvin in the bottom, and this Kelvin, I just accidentally moved it. It's right here. Kelvin and Kelvin. And that pressure you get is, thank you, 6.116 atmospheres. How would you convert to kilopascals? Yes, 101.3 kilopascals for every 1 atmosphere. So basically, you're taking 6.116 times 101.3, which rounds to 620 kilopascals. That's our final answer. All right, we'll do the next one together. Give you guys a second to read it. Start writing down your notes. We're practicing a lot of math today. Chemistry is just fun math. Don't tell my math teachers that. Yes. Okay, I'm starting 19. I'm going to just talk out loud at you here. 100 milliliters of gas is collected in a very large test tube. The weight of the gas, the weight of the gas in the test tube, this is interesting, we're given mass, okay, is 2.62 grams. We may not need it till the end of the problem, but I'm going to write it down. The gas was collected at P pressure, 697.68 millimeters of mercury. How did I even know that was pressure? How do I know it's pressure? It's millimeters of mercury, right? So I don't have to say, it doesn't have to say pressure for you to know that. Good. And then the temperature is 10 degrees C. Question, what's the molar mass of the gas collected? Ooh, this one's a little different, right? Now, molar mass. What are the units for molar mass? Grams per mole, right? Heck, we got grams. It's given to us. The grams are given to us, right? We're going to implement that when we need to. So basically, the question's not asking for molar mass, it's asking for us to get moles. Do you see? Because I can ask you any variation of this. I'm asking for moles, really, because after you get moles, you'll take your grams and divide it by the moles you get to get molar mass. It's just one extra step you gotta take. Okay, so using this knowledge, what am I solving for? N, so here we go, PV equals nRT. How am I isolating N? Divided by RT, divided by RT. So N is equal to PV over RT. Plug, plug, plug. P, what do I gotta do with P first? I got to get that to atmospheres, so you would take, you don't have to show this work, that's fine with me. You can calculate it in your calculator. You take your 697.68 millimeters of mercury times what over what? 1 atmosphere over 760 millimeters of mercury. That is a value, what is it, 0.918? 0.918 atmospheres. Okay, so that's the P we plug in down here. 0.918 atmospheres. V, is V in good shape?
No.
Nope. Gotta get it to what? Liters, good. So this is how many liters? Point what? 1, 2, 3. So 0.100, give me, liters. So 0.100 liters over, our value is a standard, 0.0821 atmosphere liters per mole, K, and T. Are you in good shape? All right, you got to add 273 to that guy, so that's 283. So 10 plus 10 plus 273 is 283 Kelvin. All right, what units do you think you're going to cancel? Everything but moles, good. Atmospheres on top, atmospheres on bottom, good. Liters on top, liters on bottom, good. Kelvin on bottom of the bottom, and Kelvin on the top of the bottom. Cancel. Leaving us with moles again. So moles is our unit, good. So N is equal to, calculator, good job guys, 0.003953. And I'm expanding out my decimals because I don't want any rounding error. You guys did a couple things on your quest that had some error. So if you round out, keep out a couple decimals more than you need to, that's fine. Just make sure you round at the very, 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 very end. Okay, here's moles. What do we do now? Question was get to molar mass. Yes, thank you. Take your mass, take mass, divided by moles to get molar mass. So mass was given as 2.62 grams divided by 0.003953 moles. Basically what it's saying is that many grams is equivalent to that many moles. If you divide them, that's the molar mass of the compound, which would be 662.8 grams per mole. Which is just a humongous number, but it's like probably like a large protein or something like a biological molecule. Okay. I have to show you how to do number 20 because I've not taught you how to do this yet. I'm going to do 20 right now. Actually, I'll wait on that for a second. Okay, take a minute stretch break. Go up and see somebody. I just have to do a little bit more math with you. Yeah. Yeah. 63. Yeah. Yeah. Stand up, stretch for a second. We got more math. More math. You can actually just write it out. You don't write it first. You can say,
It's nothing.
yeah, yeah.
Like I should
Okay, guys. Ready for these? So today I'm killing you with a little bit of math because tomorrow we're doing a lab utilizing this math, and then Wednesday we have a web class to utilize and practice this math. So I gotta teach it to you early in the week so you can practice for a couple days before you get really good at it. Okay? You have a test on this material Fridays. We're almost done. Like we're talking today, talking tomorrow. Thursday's review day. That's Friday. So it's a really short unit. Okay? So, I need to review a little stoichiometry. Write down what you want to here, but I need to kind of walk you through what you already know and connect the dots from last unit to this unit. So, we're talking about gases now. So, a lot of times gases are going to be talking about volumes. I know you love that 22.4 liters per mole number, right? But that's only true at STP. So, we have to recognize when we're given STP and when we're not. So, if I ever ask for you to, let's say, go from, I might start you off with, 2 liters of a reactant. And I want you to go to liters of a product. So how many liters of a product? You can use your mole-to-mole ratios. Your mole-mole ratios that you have like in the Townsend equation here. So there's a 2 there, a 1 there, and a 2 there. They're mole-mole ratios. And for gases, they're liter-liter ratios. It's really nice. So don't think you got to go, oh my gosh, I got to go to moles, and then I got to go mole-mole ratio, and then I got to go back to liters, because essentially you're canceling out your mole stuff, conversions. So you can go liter to liter, and that's fine. So if I told you in this problem, I'm going to show you this trick actually. There's a 2 right there, and there's 1 right there. If I told you that you had 5 liters of hydrogen gas and 4 liters of oxygen gas, and I want you to figure out how much water you can make, how many liters of water you can make, the quick and easy LR, if I don't ask you to show all your work for it, is this. You have to listen and write if you're going to write this down. In your head, I'm not going to write anything down because I don't want you to use the numbers that I'm telling you in your head. You take your 5 liters, or if this were 5 moles, you could do the same. 5 of the hydrogens divided by its coefficient. So 5 divided by 2 is what? 2.5. 4 divided by 1 is 4. Who is lower? Hydrogen. Therefore, hydrogen's the LR. Okay, so I'm using that number. That is the quick and easy, dirty way to do LR. However, I don't teach you that at first because you need to know how to do the have-need method to understand this method. Basically, what we're doing in our head is the have, I'm giving to you the have, the liters. We're doing the stoichiometric ratios, like, comparing our reactant ratios. In our head, And what we did was that when I said less, that's basically who is running out first. It's not simply because I have less of that particular number that it's the LR. It's because I've divided by its recipe, its coefficient. So what we just did was 5 divided by its coefficient, making it 2.5. 4 divided by its coefficient, making it 4. The one that was lower was the LR. So if you can efficiently do that in your head, you can proceed with the problem. If not, you'll have to do the have-need method, okay? So basically that means I take my 5 liters of hydrogen. What's my liter to liter ratio to get to water? 2 to 2. 2 liters of water are created for every 2 liters of hydrogen gas used. Right there. Guess what? I make 2 for 2 is 1 over 1, right? I can make 5 liters of water from 5 liters of hydrogen. That's pretty easy stoichiometry. That one is a liter to liter ratio. Thumbs up when you're good to move. Hey, Morgan. I'm videoing. You have to catch up, okay? Okay, so that was just a simple introductory problem. I'm going to do some more with you guys. This is just showing you can do liter to liter, no problem. Okay, now what if I give you, let's say, moles, and I want you to go someplace else? I'm videoing so you guys can go back and look at this if you need to. Let's say, and this is just a quick and easy schematic to show you this, but you can also do this in your head. If I ever give you the mass of something non-gaseous, so like I might say potassium chlorate, it's a solid ionic compound. I'm going to give you grams of that thing. Well, grams are useless to you, right? You always want to get to moles. Well, how are you going to get from moles of something to, from grams something to moles of something? What are you going to use? Molar mass, right? Okay, this is just a reminder that you know how to do stuff like this. And I want you to go to volume of a gas. Well, that gas is something that acts differently, so we use slightly different formulas for it. So if you get from grams of that solid to moles of that solid, your next step is to get from moles of solid to moles of gas. Well, how do you get from moles of anything to moles of something else? Mole ratio, right? So from moles of X to moles of gas, you use your mole ratio from where? From balanced chemical equation. BC, okay, balanced chemical equation. Okay, now this is the magic part that you just learned. You cannot, if I don't say, I'm assuming if I didn't say STP, it's not at STP. So once you're to moles of gas, this is in. Okay, this is in. So I can make you start with the reactant and you get to moles of gas, aka probably the product, and that's in. Not at STP, therefore you cannot use that mole ratio, or that 22.4 liter per mole number. So basically what you're going to have to do is and the problem, you would be given the pressure, you'd be given the temperature, you know the R value, you just calculate the N value, so you can calculate volume using your PV equals nRT. Okay, so we're meshing both stoichiometry and our new gas law we just learned today. Does that step-by-step process make sense? Okay, we're going to do some example problems with that. Basically, if I ask for gases, if I ask for a gas period, you cannot put anything about non-gases in a gas law formula because it's gases, right? So I might start you off with some solid stuff. It's useless. You got to get to moles of that solid stuff, which is still useless because it's a gas law problem that you're doing. You got to get from moles of solid to moles of gas. That's the magic number. This is N. And then in the problem, I would also be giving you P, T, and V. So if you got N, you would see that as PV equals nRT, and then you would know how to solve for volume because you know PV equals nRT now. Doing a problem will actually make a lot of sense. This is all like vague. Okay, but if you do, if in the problem I do say STP, then go with the flow. You know how to use STP. You know this conversion factor, 22.4 liters per mole. So you can always use that at STP. So basically, non-STP, you're going to be using PEV equals nRT in some way or form. And then we basically already did this part. We already know that once you get to moles of a particular gas, you can always get to grams of it by doing what conversion? Molar mass. Okay, we can get there. We're going to do a practice problem with this though. Tired Monday, the Monday blues. Okay, let's do a practice problem. This one, did I have this on your paper? Yeah, this is number 20. 20. Nope, lied. Is this number 20? Nope. Nope, lied. Okay, so let's do this together. So write down this practice problem because this is the only one I'm going to do for now. And potassium chlorate. Ooh, potassium chlorate decomposes. What is your BCE for this? KClO3 decomposes to what and what? Good. So a metal chloride and oxygen gas. Remember, decompositions constantly make gases, and guess what we're talking about today? Gases. Okay, so we know we're making gases. That's not balanced though. To here, oops, sorry. 3 oxygens here, 2 here, and 2 here. So that's how chlorates decompose, metal chlorides and oxygen. Okay, now let's finish reading. At 755 millimeters of mercury, so what's this? Pressure. And a temperature, so T is 23 degrees Celsius. And it says 42.6 milliliters of the gas. That's the volume of the gas, right? So that's V of gas. 42.6 milliliters of the gas is collected. So far we got a bunch of givens. So when potassium chloride decomposes at 755 millimeters of mercury, 23 degrees C, 42.6 milliliters of the gas is collected. Now here's our question. How much means mass, right? How much potassium chlorate, potassium chlorate must have decomposed if none of the gas was lost? So I'm going to work backwards with you here to show you that you know how to do this. It's just a new scenario. All right, we know we want to get to grams of potassium chlorate. How do you get to grams of anything? From what? From moles of potassium chlorate, right? So you know that before you can get to grams of potassium chlorate, you're going to get to moles of potassium chlorate. Potassium chlorate is a solid ionic substance. So that moles you get there, it's not coming from your gas law itself. But do I know the relationship between the gas and potassium chlorate? Do I know that relationship? Yeah, I know it's a 3-to-2 ratio. So I'm going to have this moles and the mass and to get to mass. But how am I going to get here? I'm going to get these moles from these moles. So I'm going to get moles of the oxygen gas and do a mole ratio back to the chlorate. How am I going to get to moles of oxygen gas given this information? Huh? Ideal gas law, right. So my question is get to moles of the oxygen gas, and then I can do mole ratio to get to potassium chlorate and on. But let's get here first. So let's say my question is really moles of O2 gas. So using this information, what equation am I using? Ideal, so PV equals nRT. Solving for what? N, so dividing by RT, dividing by RT. Okay, so this N though, this is moles of a gas, and the only gas in this problem is oxygen. So I'm labeling it so I don't forget this is a gas. This is not the chlorate stuff yet. All right, so my PV, this is what I'm plugging in, okay? My P, it's not in good shape, right? What is that? 0.993 atmospheres, thank you. See, I'm good with you just writing it like that. You don't have to show your work for that conversion. So that's just 0.993 atmospheres. My V, how many liters is this? How much? 0.0426 liters, because you're just taking your decimal back 1, 2, 3, so 0.0426 over R. What's R? 0.0821 atmosphere liters per mole K. And then, thank you. So 23 is Celsius. So I'm going to add 293 or 273 to that to get 296. Good. 296 Kelvin. Whew. Okay. So the ideal gas law is easy. It's just you got to make sure units are correct. All right. So you'll notice atmospheres and atmospheres top and bottom. Liters and liters top and bottom. Kelvin on the top of the bottom. Kelvin on the bottom of the bottom. And moles are left. Yay. Okay. So this is getting me to moles of oxygen gas. So whatever I get here is moles of oxygen gas. I got 0.001741 moles of oxygen gas. All right, am I done? No. Okay. So I'm expanding my decimal out because I don't want any rounding error. So that's my moles of oxygen gas. My real question is to eventually get to grams of potassium chloride. So this is the beauty of the balanced chemical equation. You have mole ratios. So if you have your moles of oxygen gas, I'm just going to rewrite that right here, 0.001741 moles of O2, get me back to potassium chloride. What's my mole ratio I'm going to be writing? 2 moles of potassium chloride over 3 moles of oxygen. Good, because you're taking this and this. So I have my moles of oxygen. I'm putting 2 moles of potassium chlorate over 3 moles of oxygen, which is just according to the balanced chemical equation. And I'm not going to actually stop there. What's my final question? The units they want. Grams, right? I'm just going to keep going if that's okay with you, because my moles of oxygen are gone. I'm in moles of potassium chlorate. Well, I just got to get the molar mass of that guy. So 40 plus 35.45 plus 48 is like 122.55 grams potassium chlorate over 1 mole. And now you can come on. Hey, we do know how to do. Okay, that's the last bit. That's all I'm going to do. Thank you for your patience. This answer is 142 grams of potassium chlorate. So, what you are seeing here is if you got stoichiometry last unit, no big deal. You're tacking on a little bit of gas law with it. You're combining them. If you did not get stoichiometry, please utilize that extra credit option to your benefit, because you need to help yourself get through that so you can mesh these 2 units together. Okay, because stoichiometry is not disappearing. It will come in and out. It's not disappearing. Okay, so the rest of the time is yours. What I want is you guys have 5 questions. You see them on the bottom of your page. It says ideal gas law stoichiometry lecture practice. See those 5? Okay, see those 5? And the answers are on the bottom. I want you to try those 5. That means you're writing down your givens, you're writing down your BCEs, you're starting the problems. Even if you can't get to the end, you can at least get 70% of the way through that problem, okay? So, I'm taking those tomorrow. So, the problem set 14, which is due Wednesday, you can start that if you want to. I'm scratching that because it's due Wednesday. I want you to do the ideal gas law stoichiometry through problems numbers 1 through 5. And we'll look at them tomorrow. I do, yeah. And then if you guys want me to do the, Messiah, go to Coach Barbie. Sorry, that's what you just called. If you guys want me to do any problems from the 1 through 16, I'll do those now. Yeah. I'm doing 1 through 16 first, and then I'll do number 20. Okay. 1 through 16. I know I gotta do number 10 and 12. Hey. See you, Miss. No, I just checked it. I went around and checked it for completion. I'll put the answer key for problem set 13 up like in a day or 2. I'm still, most of the class, some of the class hasn't done it yet, so I'm not going to check it right. I'm not going to check it orally, I mean. This was number 12 if you needed that. On the homework from last night. And I'll do number 10 tomorrow. That's number 12. Okay. That's one thing that's yeah. Yeah, I mean, start tonight if you can, but I know those are going to be due tomorrow.
When's Tuesday?
Monday and Thursday. But today I have meetings on Tuesday and Wednesday this week. But my schedule's outside. That's it. And then Tyler, share that test with Morgan.
Yeah.
Okay, you tell her about the extra credit thing.